So welcome everybody to the IFIMAC+ICMM joint seminar series on condensed matter. It is my great pleasure to present our second speaker of this series, Francisco Guinea, who is going to talk about twisted layers, narrow bands, and new phases in two-dimensional materials. I think Francisco, or Paco, as we all call him, is very well known by all of you and in the physics community in general. But nevertheless, I would like to give a short presentation of his career and merits. Paco is a senior researcher at IMDEA Nanoscience in Madrid since 2014. And previous to this, he worked for many years in the ICMM-CSIC. In the last years, he's also been a professor at the University of Manchester in the UK, and he's also currently a senior researcher at Donostia International Physics Center. During his career, he has received many honors, including the Bell Lectureship Award from the American Physical Society in 2010, the Blas Cabrera biannual Spanish National Prize for Physics in 2011, the Spanish Physical Society Medal in 2013. And Paco has worked over the years with great success in numerous subjects in condensed matter physics, but he's especially known and widely recognized for his work on graphene and two-dimensional crystals in general. He is a frequent collaborator of the Nobel awardee Kostya Novoselov and other important researchers such as Antonio Castro Neto, Nuno Peres, Vozmediano and Mikhail Katsnelson. Paco has almost 80,000 citations according to Google Scholar, and his review of modern physics, The Electronic Properties of Graphene in 2009, has almost 18,000 citations. So before giving the floor to Paco, let me inform you of a couple of things. One is that in the weekly announcement of the next speaker's talk that all of you receive when you are registered to this seminar series, at the end of the message, you will be able to find a YouTube link to the recorded seminar of the previous week. So for example, in the reminding of today, you could find the video of Stephanie Kenna-Cohen of last week. And in the announcement of the next week, you will be able to find Paco's recorded talk of today. And the second thing is that Paco has agreed that you can ask him questions during the seminar. So to do this, please, in general, have your microphone muted. And if you want to ask something, you are allowed to unmute it. Another option is that you raise your hand, and I will be checking the raised hands. And you can also write your questions in the chat, and then at the end of the talk, we can read them. So with this, I give already the stage to Paco, and thank you very much.
Well, thanks a lot, Elsa, for this very nice introduction. And I'm really glad to participate in this series of talks and so on. It is really an excellent initiative, and I'm very glad that it is happening, and I look forward to future seminars and so on. Can you see my presentation already? I suppose so.
Yes.
Okay, great. So this is what I'm going to talk about. I will focus mostly on twisted graphene and the new discoveries of a complex phase diagram and so on. And as this is more like a general talk, I will mostly highlight general features of the system and then and the work being carried out in general. And at the end, I will also mention particular issues which I think are interesting and on which we are working right now. But as I said, I will try to keep the discussion at a very general level. You probably know how everything started. That was like 2.5 years ago. At the same day, there was a talk at the APS March meeting. These two papers appeared in Nature, and they were posted in CONMAT at the same time. And that really caused a boom of a great deal of interest in twisted graphene. And since then, I mean, there are hundreds and hundreds of research papers on this, and people have been considering these systems from all possible angles, and that's what I'm going to talk about. This is a bit of a summary of the incredible repercussion this report of new features in twisted graphene bilayers had very quickly. And one of the reasons why this topic has been incredibly interesting to everybody is because it touches many different subfields in condensed matter physics and beyond. This is a summary I made way back, a few months after the discovery was reported. And as you can see, both on the theory side and on the experimental side, people with very different backgrounds got interested in this problem. And that really helped to make it a really important thing in condensed matter physics nowadays. I am not going to review very much graphene and carbon in general. That's I want to mention that carbon is a very versatile element. It has caused a lot of surprises in condensed matter physics already. And by now, we all know that, sorry, I think I have to, that there are these, there are fullerenes, which we can consider kind of spherical, I mean, graphene with a spherical shape. There is graphene, there are nanotubes, there have been Nobel Prizes associated to these discoveries, and of course there's graphite. But I will not go into the details of why carbon is so versatile and interesting. That just let me mention that on the other hand, carbon is incredibly simple. It contains only 4 valence electrons, and actually, if you look to the electronic properties of graphene and graphite, they are all related to a single orbital, which is pointing out of the plane in this bluish orbital drawn here, which is pointed out here, and that's basically all which matters. So for a theorist like me, it is very convenient to work on a system like graphene. But let me backtrack a little bit. I mean, researching graphene started in full in 2004 with the isolation of graphene by the Manchester team led by André Geim and Kostya Novoselov. And it very quickly it became a very important topic in condensed matter physics. And then slowly the interest decayed. But there was a very important change in 2011. And that was the discovery that you could use hexagonal boron nitride to encapsulate graphene and perform experiments which could not have been done before. So hexagonal boron nitride is something very similar to graphene. It has the same lattice structure. And it makes sense that it's very similar because if you look to the periodic table, carbon is somewhere, and then boron is on one side and nitrogen is on the other side. So but it shares many features with graphene, except that it's an insulator with a very wide gap of about 6 electron volts. And it's interesting to note because most of the hexagonal boron nitride, which has been used by researchers since 2011, is provided by a laboratory in Tsukuba in Japan, near Tokyo, led by these 2 guys. And if you look at, and it's for free, it's free. I mean, it's available for free. The only thing is that these 2 persons, which who fabricate the hexagonal boron nitride, appear in all the papers which have been published using their samples of hexagonal boron nitride. And nowadays, they're the most prolific and productive guys, I think, in the history of physics and maybe in the history of science. It's an interesting thing to realize. Okay, and the thing hexagonal boron nitride allowed to make was metacrystal, so to speak, Moiré superlattices. On the left here, you see an early work on Moiré superlattice created by graphene on a metal, on rubidium. And this is the first publication on Moiré superlattice due to the to the combination of a graphene layer and hexagonal boron nitride. As I said, they have the same hexagonal lattice. This is a kind of a drawing of what happens as you change the rotation angle between the two. You notice a pattern, and the pattern is cannot be any larger than this when the two layers are perfectly aligned. So you have it is a bit of deceiving, cheating, these plots I'm showing to you, because these angles do not define commensurate arrangements. So what looks to you a pattern is not a true pattern. All these blocks are different from each other by a little bit. Yeah? Okay. So the thing is that by creating these super crystals or metacrystals or Moiré patterns, people managed to probe a particular problem in, for instance, in condensed matter physics, which was open since way back in history. And that is what happens when you apply a really strong magnetic field to a crystal. That's the problem of the Hofstadter butterfly. And it required, I mean, which is plotted here, this is the original paper, Douglas Hofstadter realized that you had a very interesting spectrum which was not band-like or atomic-like or anything if you have a crystal in a magnetic field, provided that the magnetic field is sufficiently strong so that the flux, the magnetic flux per unit cell was comparable to the quantum unit of flux, which means thousands of Teslas for normal crystals. And, I mean, this is the Hofstadter butterfly for the square lattice, the original problem worked out by Hofstadter, and this is what you expect in the case of a honeycomb lattice like graphene. And it turns out that the parameters in these Moiré patterns created by graphene or hexagonal boron nitride have the right dimensions, which are outlined here, such that the unit cell, which is very large, as I said, this is a quasi-mesoscopic system, is large enough so you don't need a very large field in order to have a quantum unit of flux per unit cell. And indeed, people realize experimentally many of the features predicted by Hofstadter in his pioneering paper. This is work we did way back. I mean, there was a lot of theory work as well. Actually, it's relatively simple. The fact that the Moiré unit cell is so large allows for a lot of simplification. It's a bit like describing graphene by a Dirac equation that works very well if you're interested in properties which are much larger than the interatomic distance. Same thing happens here. The Moiré is much larger than the interatomic distance, and you can change a little bit this Dirac description and get a lot of information on the patterns, on the bands and electronic structure of graphene on top of boron nitride. You have gaps, you open gaps, which is something quite challenging in graphene. You can have secondary Dirac points, and all these interesting features have been observed experimentally. So this was the line which many important laboratories in the world were studying. Moiré superlattices made up two-dimensional materials, especially graphene. And the group at MIT, led by Pablo Jarillo Herrero, realized that there was an alternative way for creating Moiré superlattice, and that was not by playing with the substrate, but by playing with a second graphene layer on top of another layer and changing the twist angle. And that's the way these discoveries were made. This is the kind of system, this is the kind of system which was being studied at the MIT, and to the surprise of the team led by Pablo Jarillo Herrero, they found an incredible phase diagram outlined here with superconductivity, insulating phases, and whatnot. These are more, in order to show how fast the topic is moving, these two papers were posted last week, and now the new challenging thing is to arrange 3 layers instead of 2, but controlling the relative angle between the two. This is MIT, again, Pablo Jarillo Herrero. This is Harvard, Philip Kim. Both papers agree. This system also shows a lot of superconductivity. It doesn't show so many. I mean, there are different systems, of course. Each lab has their own samples. But the thing is that superconductivity is still there. It's better seen because you have Fraunhofer patterns and so on. So definitely that's good evidence for superconductivity. And there is less of other phases. But the fact that this system is superconducting is, as remarked here with strong coupling superconductivity, is already quite interesting. Now let's look at this problem in the framework of condensed matter physics, of strongly correlated system materials in condensed matter physics. And here there is a list of the typical strongly correlated materials which show a complex phase diagram and which have been studied intensively before twisted graphene. And the phase diagrams are not that different from the ones reported initially. Namely, there are insulating phases, and near them there are superconducting phases. If you look at the way things have evolved in connection with twisted bilayers, what is different in the two cases is that in twisted bilayers, superconductivity is much more prevalent than insulating phases. So most of the phase diagram, like in these two papers, is occupied by superconducting phases, unlike the situation in other more understood or better understood strongly correlated materials. Typically in these strongly correlated materials, I will go back to it later, people think that the superconductivity is not due to phonons, is due to other excitations most likely associated to the magnetic phase. And to a first approximation, the whole system can be understood as some kind of variation of the Hubbard model. I'm speaking as a theorist. Now, what about other strongly correlated features in carbon compounds? There are not that many. There is superconductivity in the graphite intercalation compounds, which are outlined here, sketched here. And they can be considered as approximations to as graphene layers separated by metals. The metals put a lot of charges in the graphene layers, so they are like heavily doped graphene. And there you have superconductivity at very high electron densities, if you translate what I am saying into a carrier density per graphene layer. And same thing happens in intercalated fully rigged. There, actually, you can have relatively high superconducting critical temperatures. There's no evidence for insulating phases in these systems. With respect to the effect of repulsive interactions, first, there is the renormalization of the Fermi velocity in graphene, which is quite interesting as well. And then at high magnetic fields, you also have a lot of broken symmetry insulating phases, but you need the formation of Landau levels. And of course, the most obvious result from strong repulsive interactions is the fractional quantum Hall effect, which is relatively easy to observe in graphene. And let me again show you what Pablo Jarillo Herrero told you. These are these two layers of graphene. And now, as I said, there is no limit of how large your Moiré pattern can be. If the two layers are almost perfectly aligned, you have a very large Moiré pattern. And as you change the angle, you can change also the size of the Moiré pattern. So let me see. Okay. Part of what happened when you twisted two graphene layers one on top of the other had already been studied theoretically in this seminal paper by Joao López dos Santos, Nuno Peres, and Antonio Castro Neto, who again took a kind of long wavelength approximation based on the Dirac model and basically describe the system in all its complexity. That model was then later on investigated in great detail for the situation when the twist angle was very small, like 1 degree or so. And Rafi Bistritzer and Alan McDonald realized that there were incredibly flat bands for some of these angles, which they called magic angles. Tight binding calculations basically simultaneously confirmed the existence of these magic angles and flat bands. This is a nice paper by Pablo San Jose, Jose Gonzalez, and myself, where we discuss a simplification of this model, of the model of Lopez dos Santos et al., where you had infinitely flat bands, not very flat, but totally flat bands. It's by switching off some of the couplings between layers. These things were observed experimentally by STM experiments, so by the group of Ivan Ray at Rutgers. And what happens is the following. I mean, this is the, now let's look, I mean, you have electrons. I mean, these systems are very clean. You have electrons in the two layers. In each layer, they are described by a plane wave, and they, from time to time, they tunnel to the layer below or above. And it's coherent tunneling, so the phases which describe the plane waves remain unchanged in the tunneling process. And the action in graphene, in reciprocal space, in Fourier space, it's at the coordinates of the Brillouin zone, at the k prime points. This is where the Dirac points are seated, and this is where the Fermi level is. And this is what matters if you want to describe graphene with a few extra electrons or holes. Now, when an electron, and then the blue and the green lines are the Brillouin zones of the two layers, and the red lines define the mini Brillouin zones of the Moiré superlattice, which is formed when you put one layer on top of the other. So one state from one layer, let's take one from the green corner, goes to the blue Brillouin zone, it is shifted with respect to the Dirac cone in the other layer. And it can be shifted in different ways, which is kind of more or less explained there. And as a result of that, when one electron, which is sitting at the Dirac cone in one layer, is transferred to the other layer, it shows up in the other layer as a superposition of three different plane waves. This is where the complexity of the problem is. Then those three plane waves can backscatter to the initial plane, and then they will become 9 plane waves and so on. So there is a very complex interference pattern associated to this multiple scattering or tunneling between layers. It's all related to the fact that what matters in each graphene layer is not at the center, at the gamma point, at the center of the Brillouin zone. Such thing will not happen if the electrons you're interested in are sitting at the center of the Brillouin zone. It's because you have two inequivalent coordinates, and that's where the states which matter reside. And it is what Rafi Bistritzer and Alan McDonald discovered. This alpha square is a proxy for the twist angle. And if you look at, I mean, the bands, they always have Dirac cones, mini Dirac cones, like in the case of hexagonal boron nitride. But the Fermi velocity at those Dirac cones, from time to time, it vanishes. And because of that, you have very narrow bands. This is the situation as you change the angle. You see the band becomes narrow. There is a band which becomes narrower and narrower and narrower, and then it becomes starts to get wide, and the gaps between this narrow band and the other mini bands disappear. The bandwidth, you can define the magical angle in terms of the vanishing of the Fermi velocity, as Bistritzer and McDonald did. You can define the magical angle in terms of the bandwidth. They coincide more or less, and there are a number. There's a magical angle when the twist is about 1 degree, then there is a second one when it's about 0.8 degrees, and many more at lower angles. These are calculations we did when we got interested into all this. These are tight binding calculations. So here you're dealing with real atomic orbitals, which is less fancy than the continuum model wrote down by López dos Santos et al. But the result is the same. This is not even a magic angle, it's a commensurate superlattice, and you see a narrow band here, and this is a blow up of that narrow band. So in that respect, the twisted graphene looks like, for instance, a heavy fermion, which are a material which also has a very narrow band. But there is a big difference, which was pointed out by these two people shortly after the discovery by Pablo Jarillo Herrero of all these interesting properties in twisted bilayer graphene, namely that depending, so this is the band, but the charge density associated to different states in this band is very different. That's pointed at these are our tight binding calculations. So depending where you are in this band, you have very different charge densities. That doesn't happen in a heavy fermion, for instance. In a heavy fermion, the charge density associated with a narrow band is mostly residing in some f orbital in a rare earth or something like that. And it's always there, no matter where in the band you are. This is another plot of the same thing. And when you go to lower angles, the situation becomes even more complex. You have more Dirac points, more Van Hoff singularities, and the bands become really complex. That was pointed out by these authors there. And you can, as I say, you can even simplify further the model. You can switch off some of the hoppings, and then you have something interesting because you can define it as a Dirac equation with a vector potential. But the funny thing is that the vector potential has a layer index, which is associated with these matrices here, and these components don't commute. So it's a non-abelian gauge field, which is really complex to solve. But the interesting thing is that you can also show that there are totally flat bands in this model. So not partially flat, but totally flat. That was rediscovered in this paper, and moreover, these people made connection between these flat bands and the other flat bands that you have in another famous setup in condensed matter physics, the Landau levels in a magnetic field. So there is a connection between the flat bands on one hand and the Landau levels you have in a two-dimensional electron gas or in graphene itself, for instance. So again, let's compare what's happening in twisted bilayer graphene with what happens in other strongly correlated systems. Here there are some examples. And this is the right side is something, an example taken for the cuprates. You have a very narrow band because, I mean, here you have copper and oxygen, and the electrons tunnel from copper ion to copper ion, and because it's a second order process through the oxygen, the bandwidth is relatively small. And moreover, the excitations are heavily dressed. So they have, I mean, they are damped and they need dressed by, the electrons are dressed by excitations of the magnetic background, which is outlined here. And because of that, the band becomes even narrower. And that's the origin of the narrow band. More or less, this is the origin of the narrow band in the cuprates. The situation is completely different in twisted bilayer graphene. The narrow bands I have shown to you have there are no interactions included in the description whatsoever. The Hamiltonian is much simpler than the Hamiltonian used to derive the narrow bands is much simpler than the Hamiltonian you need for the cuprates, for instance. With a couple of parameters, that's enough. And all the energy scales you plug into the Hamiltonian are of the order of 100 MeVs or more. However, at the end of the day, you have these very narrow bands whose width is a few MeVs. And there is another interesting regime at much narrower angles. The situation changes dramatically, and then you have a succession of, you have a totally different pattern. You have very big Moiré unit cells, but with totally different patterns with quasi one-dimensional channels. I will not have the time to discuss it. This is not working. Okay, there is an animation in one of our papers on what happens in this limit, and that's being extensively studied. I think it's another interesting situation, but so far, the complex phase diagram and all that has been found only for twist angles, like 1 degree or something like that, and not for the very low angles, which I have mentioned to you before. And now, as a theorist, I just want to mention that the complexity of the system allows you to look at it from at least these 3 different angles. You can think of it as a variation of the Hubbard model, but then I will discuss it later. You need to deal with how to write the model in terms of localized orbitals. I mentioned already, you can look at the model like some variation of the Landau levels you have when you have a 2-dimensional electron system in a magnetic field. And there are very sharp peaks in the density of states, Van Hoff singularities, which moreover, they proliferate as you change the angle. So you can look at the twisted bilayer as extended wave functions, but with very high peaks in the density of states. And the fact that these 3 completely different alternatives are available for the description of twisted bilayer graphene is what makes it interesting. It really highlights the complexity of the problem. Okay, as I mentioned, if you want to start with the most studied, procedure we use in strongly correlated systems, namely Hubbard-like models, you need to go from a plane wave description, which is what I've been talking about before, to localized orbitals. That's very easy to achieve in the cuprates because you know what the localized orbitals you have to consider. Those are the orbitals in the copper ions and p orbitals in the oxygen ions. Here it's much more complicated because in the unit cell you have not 2 or 5 interesting orbitals. You have like 10,000 carbon atoms, and each carbon atom has 1 orbital. So you have to deal with all these very many orbitals. But the usual procedure to go from extended states to localized states is to define Wannier functions, and that proved to be not trivial at all. That was carried out in these very interesting papers I am showing here. And the outcome is this cartoon here. You have, the underlying black lattice is the Moiré superlattice. So each hexagon has dimensions of about 12 nanometers or so. I mean, the size of the side of the hexagon is about 12 nanometers. It's mesoscopic. It's not atomic-like. But the Wannier functions are centered at the corners of this real space unit cell, but they are basically 0 at their centers. And they extend far away into the center of the unit cell. And moreover, they seem to overlap with each other. That cannot happen, but Wannier functions by construction are orthogonal, but they definitely are defined in the same region of space. Again, I emphasize that is very much unlike what happens in typical strongly correlated systems. Moreover, there is a problem with Wannier functions, which is outlined in this very nice review paper, namely that they are not uniquely defined. There are many ways to define a Vanier function. A Vanier function basically is an integral over the block waves, but you can add a phase to the block waves and you have another set of, Vanier functions. That's what I'm trying to say. That was pointed out way back by David Vanderbilt, who has done a lot of work on how to define Vanier functions and so on. And that led to something which was pointed out very quickly in connection with twisted bilayer graphene, which is the so-called obstruction. Namely, that the best Vanier functions you can define in twisted bilayer graphene, respecting a lot of symmetries, which are good something good to do, are not very localized, to say the least. What I mean by that is that the expectation value of R squared blows up, is infinity. So that which implies that the Vanier functions are not exponentially localized like nice atomic orbitals do. They have power law tails, which look like that. That doesn't mean that the Vanier functions are not normalizable. It just means that the expectation value of some operators blow up. Then we have discussed it. The obstruction is relevant or irrelevant has been a topic of intense discussion. We think in this paper that is not that relevant because typically you use your Vanier functions, your localized orbitals, to describe different interactions, which at the end of the day are matrix elements of Hamiltonians or things like that. You never encounter operators which blow up like R squared. Typically, the operators you are interested in real space are bound, and this obstruction is not such a severe difficulty with a local study of twisted bilayer graphene, but it's on the eye of the beholder because other people think otherwise. And now let's look at numbers. Let's look at the interaction. By the way, this is an early paper. Pablo San Jose, Luis Gonzalez, Ardaga, and I did some time ago. But this is the typical Moiré unit, lattice unit you have for a twist angle of 1 degree, which is when things become really interesting. It's 15 nanometers. So I emphasize this is a metamaterial. It's a metacrystal. However, because of this weird charge distribution, it turns out that the charge distribution, when you dope the system, you don't dope it. I mean, the charge distribution is not homogeneous within the unit cell. It's localized within a much with a much lower radius than the lattice unit itself. As a result of which, when you dope the system, you have to pay a large price in Coulomb energy. It's a bit like a quantum dot. And if you look at other terms, like the one we consider here, the on-site atomic repulsion, and you project it into these flat bands, this is it is still large compared to the bandwidth, but it's less. But what is really remarkable is that this scale is much larger than the bandwidth itself. So definitely these systems are strongly correlated no matter how you define this. Now I will focus a bit more on our own work. This is again this picture, depending on which state you're looking. You can have, I mean, this is a state this is the band. This is the mini Dirac point you have, and this is the charge density associated to the states at this mini Dirac point, and at the gamma point, which is the center of the mini Brillouin zone, you have the opposite. You have a minimum at the center of the unit cell, while here you have a maximum. So because of that, you are creating, to a first approximation, if you just look at the electrostatic potential, which is generated when you go away from neutrality, which is what you do by applying gate, you are creating a very strong, on the scale of the bandwidth, electrostatic potential. And what does it do? It couples to these states, which are different at K and gamma. This is an early calculation. And it totally, I mean, the red lines are the original flat bands as described by Bistritzer and McDonald. And as soon as you move away from charge neutrality, these bands are very strongly distorted. This is very much of an understatement. Here we were putting a very low, very small electron-electron repulsion, but nevertheless, you see that the bands are totally distorted. And it makes sense because the charges at the gamma point are very homogeneous and they average out the electrostatic potential, and because of that, the energies at these points don't move a lot when you move, you go away from neutrality, but the charges at the K and M points are very much localized at the center of the unit cell, and because of that, they are pushed by the electrostatic potential. Again, I emphasize that is another crucial difference between a twisted bilayer graphene and typical strongly correlated systems. In a Hubbard model, if you increase the number of electrons, the whole band is shifted rigidly, and that's the end of the story. So what does it imply? This issue of changing the shape of the bands when you put more or less electrons was discussed way back in connection with the couplets by Jorge Gis and collaborators. It is called electron-assisted hopping. And in terms of a tight binding description, it implies that if you have your Vanier functions, the hoppings you have are dependent on the number of electrons you have as well. And we pointed that out in our paper, and that has been also discussed in other papers. And it makes sense because, as I said, your Vanier functions are spread out over the entire unit cell. So even if they don't overlap, when you turn on an extra potential, it will have matrix elements between different Vanier functions. It will not be a local operator like it. I mean, the electrostatic potential will always consider it as some kind of local perturbation. But in these very strange Vaniers, it needs not to be a local perturbation. It actually includes a kind of hopping between different Vanier functions. This is a cartoon of what I'm trying to say. This is the kind of thing you may have. You have two Vanier functions, and there is some hopping. This is what Jorge has discussed. If you put charges here, for instance, this orbital may be more spread out, and because of that, you're changing the hopping, and then you're changing the shape of the band. Then this kind of thing is you can write in as a hopping term, which depends on how much charge you have around. You Fourier transform it, and then because there are hoppings involved, you have cosines and sines. And that means that your interaction can be either attractive or repulsive, because the cosine can be either positive or negative. So Jorge Gis, in that respect, was perfectly right. This is an interaction which favors strongly superconductivity. And if there is a system where you can make a case for electron-assisted hopping, is twisted bilayer graphene. You can justify, you can use cook up simple tight binding models based on the Vanier description I described to you before. You add an extra term, which is this electron-assisted hopping, and you get a cartoon of the kind of shifts we observe in more detail Hartree or Hartree-Fock calculation. By the way, this is not the first time such term has been discussed in connection with graphene. Way back in bilayers, people doing ARPEs found out that the hopping between the two layers was depending on the amount of charge you had, but this topic was never pursued. Okay, these are other calculations with more realistic interaction strengths. And this is the original Bistritzer-McDonald flat band, a few MeVs in width. And as soon as you move away from charge neutrality, these bands are totally distorted. And same thing happens with the density of state. And you have a rather complex Fermi surface also depending on density. Now there is, so far I have discussed the simplest approximation to the interactions in condensed matter physics, namely the Hartree approximation. The obvious continuation is to perform a full Hartree-Fock calculation, and the Fock term is also, the exchange term is very interesting. It was already interesting in graphene because graphene, as I said previously, is a Dirac system and with a Fermi velocity, and when you have long-range interactions, it resembles very much quantum electrodynamics. And in the case of quantum electrodynamics, there is a dimensionless fine structure constant whose value is 1/137. in graphene, this constant is between 1 and 2. But in twisted bilayer graphene, because the Fermi velocity is so low, it can be like 100 or something like that. So one needs to do a full Hartree-Fock calculation, and we did it, and the situation becomes even more complex. And now you can start to explain the insulating phases people have observed. Because, for instance, here near half-filling, this Fock term changes significantly the bands, actually, because basically it's all what matters. The Hartree term is 0. There's no charging here at neutrality. But the Fock term, which is something typical in condensed matter systems, opens a significant gap, and then it makes the system insulating. And if you go away from charge and neutrality, the situation is more complex, because then you have the Hartree term, which is actually much stronger than the Fock term. I mean, the Hartree term is all electrons interact with, is due to all electrons interacting with all other electrons. And in twisted bilayer graphene, there are 4 types of electrons, because there is the Valley degree of freedom and the layer and the spin degree of freedom. So and the Fock term is an interaction between electrons and between wave functions which overlap. So that means that they have to be in the same valley and have the same spin. So then the situation becomes more complex, but definitely you have highly distorted bands which do not resemble too much the original flat bands you have in the absence of interactions. So, and as I said, you can start to write down some kind of phase diagram, including insulating phases which are spin or valley polarized, or either magnetic or valley polarized, which is similar to magnetic but not quite the same. And then the interesting thing is that you will be jumping from phase to phase. You can have phase separation, coexistence of different phases. I mean, it allows you definitely for a very rich phase diagram, which actually resembles some strongly correlated systems, the so-called colossal resistance compounds. My time is going to finish soon, so let me mention that similar results have been reported in all these references I'm showing here, namely that the bands are strongly distorted, but more interestingly, experimentally, STM experiments like here, or compressibility experiments like here, they have reported bands which are much wider than the bands you find in non-interacting calculations a la Bistritz and McDonald. Now there are other situations, let me discuss this now briefly. There are other situations where you can also have flat bands and you can create those flat bands by stacking graphene layers. One is a bilayer graphene on top of HBN. People have reported even superconductivity in these systems. We have done calculations including interactions, and this situation is totally different from twisted bilayer graphene. There is a lot of work done on graphene tri-layers, but with no twist, on a substrate, and people have reported ferromagnetism and superconductivity there. We also have studied it again. The bands are shifted more or less rigidly, as shown here, as function of filling. You don't see a big change in the bands. So definitely, in some jargon people are using here, these are type 2 flat bands, so to speak. And finally, there are these 2 papers, again, one from Harvard, the other from MIT, on twisted double bilayers. One of them, the Harvard team, reports superconductivity. The MIT team doesn't find any superconductivity. We again looked at this, and again, the bands are rigid and they're very different. Again, they are also type 2 flat bands, so to speak. Moreover, one can do more things. One can study in full the effects of the substrate. And again, the bands, which are initially very narrow, are very strongly changed, as reported in this paper. And in order to highlight how fast the field is moving. We reported this in May this year. And the main point is that the flat bands disappear if you consider situations where HVN is aligned with a twisted bilayer. And since then, 4 more papers reporting basically the same results have been posted in CONMAP. The same thing happens with, this again, the movie doesn't seem to be working too bad. Here we have a nice movie on what happened with strains. It's another recent paper where our French collaborators have put together a lot of experimental data on the strains you actually have in twisted bilayer samples, the samples people are studying. And again, this as reported in this theory work by Liang Fu and collaborators, the bands are totally changed. The width has nothing to do with a few MEVs and so on. So the outcome of all this is that these flat bands are very fragile with respect to interactions, with respect to strains, and with respect to the substrate, and so on. Okay, this is, I think, more or less, is a good moment to finish. This is what I wanted to tell you. First of all, that the leading interactions in twisted bilayer graphene, now I will report our own work, is the long-range electrostatic interaction. Second, that this interaction changes a lot the shape of the flat bands, which are no longer that flat. And third, that there are in graphene stacks, you can have flat bands of many types, but not all flat bands are created equal, and definitely twisted bilayer graphene with a twist angle near 1 degree is a particularly interesting and special case. So the twisted bilayer graphene is a very unique material, and there are a large number of open problems. And by the way, if you want to have a look to a very nice Moiré superlattice, you just need to look at the facade of the IMDEA building, because this is a very beautiful. I don't know if it can be appreciated very much in this picture, but definitely it's a nice triangular superlattice. Thank you.
Thank you very much, Paco. Maybe you can unmute your microphones to do an applause. Thank you. So, very well, Maria Jose, I think, can you unmute the microphones?
Now people can unmute themselves.
Okay, very well, thank you. So let's go to the questions for this talk. So, well, I see a question in the chat, but I also encourage everybody to please interact. Well, I see Alfredo is also raising a hand. I'm going to give the floor to Alfredo. So please, Alfredo, ask.
Okay. Hello, Paco. Thank you very much for this very nice and clear presentation. I wanted to ask you about the two bands model that you use for describing the phases and the phase diagrams. Mm-hmm. So then you know that this is there's been all this discussion whether these two bands are not respecting the symmetries of twist bilayer graphene and the problem of the fragile topology that you also mentioned. So do you think that analyzing the phases using these two bands models can have any problem related to this not respecting the proper symmetries and the fragile topology?
Good point. As I said, there are different opinions in this respect. I will mention my opinion, which is backed up by results in this paper. As I said, it's totally true that if you want, I mean, there is this question of the valid degree of freedom, which is a very good approximation at what happens in twisted bilayer graphene. If you want to have Barnier functions associated to individual values, you run into the difficulty that there is a power law tail. But still, but these Barnier functions are still normalizable. So it depends which kind of quantities are do you want those Wannier functions for? For instance, if you want to describe the Hartree potential I just discussed before, this power law tail, I think, is pretty much irrelevant. What matters are the details of the Wannier functions at the core of the Wannier functions. So in my opinion, it depends which physical quantities are you interested in. Definitely, if you are interested in an operator like R squared, you have a problem. Otherwise, I think you don't. And here we are comparing a very simple model for Wannier functions for superlattices, and in particular twisted bilayer graphene, with full calculations of the same expectation value, and the approximation worked very well. But as I said, if you ask other people in Harvard or Princeton, they will have other opinions.
Okay, yes. Thank you, Paco. Thank you.
Okay, let me read a question by Musa Hussein. Does the lattice mismatch in the heterostructure of the 2D system affect the stability of the system, or is it better to reduce lattice mismatch?
Okay, that is a totally unsolved mystery. I mean, these twisted bilayer, for sure, they are not the ground state of the system. The system can always relax and change a little bit the angle, rotate a little bit, and you will go to a phase with much lower energy. And actually, a lot of experimentalists thought that one could not have a twisted graphene with a twist angle of 1 degree or so. It was too small, and it's too easy for the graphene layers to rotate back into place. The reason why these metastable situations are pretty stable at the end of the day is a mystery. I was told informally that, for instance, the experimentalists sweep defects like bubbles to the edges of the sample, and they're like little nails or stacks which fix the layers and induce strains, because it's also true that all these twisted layers, they have non-negligible strains, as I tried to explain. So it's a very good question, which is more related to soft condensed matter physics problems. Why you can have samples with a twist angle of 1 degree or so, and why the whole system doesn't disintegrate somehow or rotates back to place, that's still a mystery.
Very well. So now, María Ángeles Vozmediano, please.
Yeah. Okay, thank you. So Paco, I'm puzzled by this value of the interactions of the coupling constant in this system, because you mentioned that due to the Fermi velocity smallness, that can be 20 or whatever. But could it happen, as it happened in fact in graphene, that although the estimated interaction is like 2, we only see very perturbative physics? Or how do we get the real value of the coupling constant, which graphene is not E square over VF?
Okay, good. Full calculation is still to be done, to tell you the truth. Of course, there are Dirac cones, but they're very narrow Dirac cones. I mean, when you describe graphene as a Dirac system, you have also to put a high energy cutoff beyond which the Dirac description that ceases to be valid. Here, this cutoff is also very small because the whole band is very narrow. So there is a competition between a low cutoff and a very low also Fermi velocity. And the whole point has not been sorted out. As I said, our calculations to a first approximation show gaps at half filling. And if you remember the calculations done for very strong interactions for a Dirac system, you could also open a gap. There is always a non-perturbative regime beyond the the regime where renormalization is valid, where you open a gap. The Dirac cone acquires a mass. Who knows? Maybe that's the situation.
A little short question, very short. Is ARPES available with these encapsulated samples or not at all? Just
Sorry?
Would be wonderful to see the real band. So is ARPES available with these encapsulated samples?
They are starting. Yeah, it seems to be complicated. For instance, the problem with STM experiments is that they are not encapsulated. Nobody has seen superconductivity in the same samples they use for ARPEs. So it's a mystery whether the encapsulation, how big the difference encapsulation makes.
Okay, thanks.
Very well. And now Sergio Ulloa, please.
Yes, thank you. Paco, thank you very much for a nice talk. I have a question on, I mean, what is your opinion then on what drives the superconductivity? Because you're kind of making an argument that it is electron-electron interactions, not electron-phone. No?
All right, good point. So far, you have all possible mechanisms available. People have put forward phonons. Also, as a bit like in the cuprates, excitations of broken symmetry, magnetic phases, and similar things. And there is the possibility of this electron-assisted hopping as well. I would bet more for electron-assisted hopping. It's unique to twisted bilayer graphene, but if it were phonons, for instance, you would expect to see the phonons are the same in all the other flat bands made from graphene layers I have discussed, which are not twisted bilayers. So you have the same phonons, you have flat bands, so why not superconductivity there? And most experimentalists don't believe in the reports of superconductivity in these systems. The excitations near the insulating phases is another possibility, which is being very intensively studied now. But it turns out that there are experimentalists who have found superconductivity without insulating phases. So it's hard to claim that it's crucial to have insulating phases in order to have superconductivity.
Now, presumably, they will have different behavior for screening. So how are the experiments with changing screening backgrounds? And
unclear. There are some, yeah, that's a good point. That's still unclear. There is only one set of experiments by the method of Atikfo in Barcelona, where they have studied the problem, and I think they don't have a clear conclusion. Definitely the insulating phases go away, and the superconductivity seems to go away, but less. So superconductivity survives better than insulating phases, but they cannot change that much the screening yet. Maybe in the future it will happen.
Okay, thank you.
There is another question in the chat. I think it's kind of related to the previous one by Jian Yu. What is the origin of the flat bands? Is it only comes from the modulation of the interlaying hopping?
Yeah. To a first approximation, that's the answer. Yeah. This. Sorry, I'm going to the model itself. Okay, sorry. Yeah, if you look at this model, which was already written in 2007, shortly after the graphene fever started, it's all there. You can go from this model to this study for very narrow, for very small twist angles, and the flat bands are already there. So a good, simple, intuitive physical argument is difficult to give. But the fact is that this complex interference between electrons jumping from layer to layer is all you need to get flat angles. Now, if you could, for instance, prove that the situation resembles somehow to a single graphene layer in a magnetic field, then you can say, okay, but then you are creating Landau levels. And this is the line which I said some people are following. But that work is still very much unfinished, and things are very much unclear. But definitely, if you use this method, write a Hamiltonian, diagonalize it, and so on, you get flat bands, that's for sure.
So very well. There is another question by Pablo. Please go ahead.
Hello, Paco.
Hi.
Thank you for the talk. This is just a short one. Do you think this has any relevance to, early reports of superconductivity or potential high temperature superconductivity in graphite?
Good.
Remember the story?
Pablo Esquinazi et al.
Yes.
I don't think so. It's true that people like Gregory Volovic claim that they are related, but then he also claims, as you well know, a good way of getting a flat bands in graphite, which we knew from the start, is rhombohedral graphite, which has flat bands at the top and bottom surfaces. And Gregory Volovic has been claiming that those flat bands may harbor superconductivity for many years, and that maybe stacking defects is what explains Pablo Esquinazi's experiment. But people are studying also rhombohedral graphite right now, or small stacks of rhombohedral graphite, and there's no report of credible superconductivity whatsoever, except for what I mentioned there, which is a tri-layer, ABC tri-layer, aligned with the substrate. And if you ask many of the other experimentalists involved in twisted bilayers, they don't track those experiments. They claim it's what they call Joule heating, not superconductivity.
Okay. Thanks.
Very well. I have a question too. You've shown us a lot of results on twisted bilayer. Now there are also twisted tri-layers. Should we expect a trend like 4 or 5 layers, or in particular, what happens when you go to N twisted layers? Are there some?
Then let's go to these recent experiments. These two experiments are actual experiments on a tri-layer, which is a superconductor. But the situation is such that the angles between the first and the second layer and the second and the third layer are the same, but of opposite side. And then this problem reduces to a Dirac equation plus a twisted bilayer. So it's not a big surprise that you have superconductivity so you look at the even and the odd combination on the top of the top and bottom layers, you can write the problem as a combination of an effective single monolayer and an effective bilayer. So this doesn't take you away. We have worked on the opposite situation, and also Andrei Bernevis and Shankar Das Sharma, a situation where you change slowly the twist angle in the same direction, and there you don't have flat bands, so you don't expect at least theoretically, you don't expect superconductivity.
Okay, that's interesting. And then another short question, I don't see anybody else asking. So you've shown us a very interesting transparency where you see these 3 theoretical approaches or mappings to this problem, the Hubbard model, the Landau levels, and the Van Hoff singularities. And just in this connection with the Landau level picture, should we expect like edge states in these flakes similar to?
Good point. Sorry, it was at the beginning. And I don't remember what this. Okay, I will answer anyway. That's a good point. Edge states, if you break valley symmetry, for instance, you will have most likely them, because then you have something like a Haldane model. I don't remember what. So edge states, I mean, non-trivial topological features you have in these systems for sure. But how close is the resemblance between Landau levels and the flat bands, even in the chiral limit, which is this limit to which Pablo, Jose Gonzalez, and I cooked up? It's very unclear to me, and believe me, this is a question which I'm very much obsessed with. What is the relation between Landau levels and the flat bands we discover, and then Ashwin Viswanath et al. Rediscover, and so on? There's most likely some connection, that's for sure. But I am not very convinced that that has been settled yet. But what is true is that other people, also in Harvard and in Berkeley, Mike Saletter, they directly describing twisted bilayers as Landau levels, and they claim it's reasonable. How reasonable it is an open question.
So if it's topological somehow, like the Hall effect, is this related to the obstruction of the Vanier functions? That
absolutely, yeah. The Vanier obstruction means that you cannot define a nice smooth set of wave functions which are continuous throughout the interval one. So you need to have a singularity, because, I mean, as soon as you have finite Chern number, which is the case, as soon as they have a non-trivial topology, you cannot define Bloch waves throughout the interval one zone, which are totally continuous. I mean, the connection between them is smooth. So you need singularities. Those singularities, you Fourier transform them back into real space, and you have power law tails. So that's precisely the obstruction.
Okay. Thank you very much. So if we don't have any further question, let's thank the speaker again. Please unmute your microphones. Thank you very much, Paco. Wonderful talk.